Section 3.4, Velocity and other rates of change. The derivative can also be thought of as instantaneous rate of change. In previous sections, we've learned and seen how the derivative can represent not just average speed, but can actually allow us to get instantaneous speed. In the next coming examples, we're going to see how the derivative can represent rate of change at any given time or x value. In example 1, we're going to talk about enlarging circles. So the first thing we're going to do is we're going to find the rate of change of the area of a circle with its respect to its radius r. So the first thing we need to do for this problem is write down the formula for the area of a circle. So area equals pi r squared. And now what we want to do is take the derivative with respect to r. So we take the derivative with respect to r. And that's why this is d dr and not d dx. It's d dr because, again, we're taking it with respect to r. So on the left side, I get that this is dA dr. And this is equal to. And so it's important to point out what the variable is that I'm taking the derivative of. So this says dr. And so I'm going to take the derivative with r being my variable. So this 2 is going to come down to the front. So I get this is equal to 2 pi r. And that's it. So then the rate of change for area of a circle is represented by 2 pi times r. In part B, we're going to evaluate the rate of change of A at r equals 5 and r equals 10. So I want to know how fast is the area growing or decreasing when r is equal to 5 and when r is equal to 10. So recall from part A that dA dr is equal to 2 pi r. So I want to find dA dr when r is equal to 5. So this is going to be 2 pi times 5, which is 10 pi. If I want to find dA dr when r is equal to 10, then all I have to do is plug in 10 for r, and I get 20 pi. What units would be appropriate for dA dr if r is measured in inches? And so we get dA dr is equal to, and let's think about it for a second. What does dA represent? This represents area. And more importantly, the derivative is the change in. So we're going to talk about the change in area. And dr is the change in our radius. So area is given in inches squared. And dr is given in inches. Now what you don't want to do is cancel these off. Because in English, we read this as inches squared per inch. So for every inch that we increase the radius, we're going to increase so many inches squared. And that's very important to know. Alright, so on your own, I want you to write the volume of a cube as a function of its side length. I want you to find the rate of change of the volume with respect to sides. I want you to evaluate the rate of change of the volume when the side length is 1 and when side length is 5. And if s is in inches, what would be the appropriate unit for dV ds? Alright, let's give this a shot. Okay, so the first thing we want to do is write the volume of a cube as a function of side length. So the first thing I'm going to do to make my life a little easier is I'm going to go ahead and draw a cube. Alright, so now that I have my cube, I'm going to label this as length, width, and height. But I do want to point out that all of them are the same. So we have that volume is equal to length times width times height. But I'm going to represent that as just side length. So I get volume is S times S times S. So volume is S cubed. And so the next thing I want to do is I want to find the rate of change of the volume with respect to the sides. So I have volume is equal to s cubed. So I take the derivative of both sides with respect to s, because it's respect to the side length. So I get dv ds is equal to 3s squared. And now I want to evaluate the rate of change of the volume at s equals 1 and s equals 5. So I get dv ds at s equals 5 is equal to 3 times 5 squared, which is going to be 75. And I get dv ds at s equals 1 is equal to 1 squared, which is just 3. So when the side lengths are 1, it's increasing by 3 and whatever the units are. And when the side length is 5, the volume is increasing by 75 and again whatever the units are. If s is in inches, what would be the appropriate units for dv ds? So dv ds, well, the volume is given in inches cubed, and the side length is just given in inches. So this is equal to inches cubed over inches, which we would read as inches cubed per inch. So for every 1 inch that the side length is increasing, it's increasing by 1 cubic inch in volume.